Internal energy of an ideal gas. The internal energy, capital U, of an ideal gas is the sum of the energies of all its particles. The kinetic molecular model of an ideal gas shows us that the total translational kinetic energy of a gas is K translational equals 3/2 nRT, and from the ideal gas law that PV equals 2/3 kTr. The average translational kinetic energy per particle is kTr average equals 3/2 kBt, where kB is Boltzmann's constant. Translational kinetic energy is due to translation, which is motion through space due to a velocity. A monatomic gas consists of single atoms which only have translational kinetic energy. Since an atom is free to move in each of 3 dimensions, x, y, and z, it has 3 degrees of freedom. A diatomic gas has molecules that consist of 2 atoms. A diatom can translate, with its center of mass moving with velocity v, so it has kTr, but it can also vibrate and rotate, so it has 2 additional degrees of freedom, hence 2 additional components of kinetic energy, namely k vibration and k rotation. Thus, a diatomic gas has 5 degrees of freedom. We now apply a basic principle in physics called equipartition of energy, which means that each degree of freedom has equal energy, and in an ideal gas there is, for the gas as a whole, half nRT per degree of freedom, and per particle, half kBt per degree of freedom. So a monatomic gas with 3 degrees of freedom has internal energy U equals 3/2 nRT, with Kp average for particles equals 3/2 kBt. And a diatomic gas with 5 degrees of freedom has U equals 5/2 nRT, with Kp average equals 5/2 kBt. These are very important results, because they show that internal energy is a function of temperature only and not of any other state variable, such as pressure or volume. It depends only on T. Now let's look at the heat capacity of an ideal gas. For a gas, we will work with molar heat capacity capital C rather than specific heat capacity lowercase c. A small amount of heat dQ added to a gas is related to the temperature change that results by dQ equals Nc dt, where N is the number of moles. Previously in calorimetry, we encountered the specific heat capacity applied to solids and liquids, both of which are completely or nearly incompressible. A gas, on the other hand, is compressible, and this adds complexity to its heat capacity. A gas does not have a single molar heat capacity because it depends on the process by which T changes. In particular, we distinguish between molar heat capacity Cv at constant volume and Cp at constant pressure. If the gas keeps its volume constant as heat is added and temperature T changes, then dQ equals Ncv dt. In this respect, a gas at constant volume behaves like a solid or a liquid at constant volume, and the heat adds to the internal energy, so the change in internal energy is du equals Ncv dt. Since for a monatomic gas U equals 3/2 nRT, we have du equals 3/2 nR dt, so we see that Cv equals 3/2 R, which is equal to 12.57 joules per mole per Kelvin. A diatomic gas has U equals 5/2 nRT, so du equals 5/2 nR dt, and Cv equals 5/2 R, which is equal to 20.79 joules per mole per Kelvin. We will revisit the topic of heat capacity after we have studied the first law of thermodynamics.